We are Group S and we are here to present our solution to robust journey planning. Most route planners do not take the risk into account. Although some journeys are supposedly faster based on the schedule, that is not always true in practice. This slide presents the general idea of our model. First, we do data wrangling and build transfer tables by transport or walk. We use transfer these tables to build the directed graph and a greedy algorithm to plan a two-phase journey. In the end, we visualize the M-fastest schedules, and we do delay analysis and robust planning based on a negative exponential distribution. We have two distinct types of data. One is the scheduled timetable of the trips, and the other one is the collected data with actual arrival and destination times. We use the scheduled times to find several possible paths between origin and destination. We use the actual data to later predict probabilities of missing connections, allowing us to choose from the set of paths found beforehand. First, we filter out the stops that are more than 15 kilometers away from the origin station, compute the possible connections done by walking at most 500 meters between stations, and filter the data to only include business days. In the end, we have a constructed table that can be used to build a graph. The graph has the stops as its nodes and the connections between stops as its edges. The edges contain the time it takes to travel between the nodes as features.
Our journey planning has two phases. In phase 1, we find the key shortest path, and in the second phase, we find M-fastest journeys based on the key shortest path. Because there could be many journeys at different time on single path, so we greedily find the best journeys for each path from tail to head. Because we have the user-desired arrival time as the tail, and we compute pair by pair. To be more specific, we build a directed graph and find key shortest path by network X. Then to find the journeys, for example, of top 2 shortest paths, and for route 1, we first process P5 to B. We filter the transport table so that the subtable only contains the trips that stop 1 equals to P5 and stop 2 equals to B. In this subtable, find the trip whose arrival time is most close to our current arrival time. And because this is the last trip, current arrival time is the user-desired arrival time at B. And by most close, we mean most close but earlier, so we make sure we won't be late. Then we set the current arrival time as the departure time of P5. Then we find the best trip from P4 to P5 by computing which trip arrived at P5 as close as the time with departure from P5 according to our previous decision. So basically, we iterate until A. It's like a greedy algorithm. In this way, we make sure both our next trip is as close as the last trip, and we won't be late between trips. And when we iterate until A, we get the whole schedule from A to B. The same for the second shortest path, and so on. After finding all the shortest paths on this path, we can rank the duration and select M fastest. Here we can tune K and M based on how many journeys we want.
To calculate the probability that the user could get to the destination on time, we build this predictive model. Here are some assumptions we made for this predictive model. And we use negative exponential distribution to model the delay distributions, since the distributions are skewed and also based on previous research. To validate our assumption, we also made the simulated data. You can see that it's very close to the real data. And also for the factor, we consider day of week and peak and off-peak time. And finally, we only pick the peak and off-peak time to include it in our predictive model. And here is the final delay distributions. And for stops with historical data, we use the accordingly mean delay and also the CDF to calculate the probability. And for road probability, we use the products of probability of each passing the road. We also consider about early departure, but because the mean for most stops, the mean is equal to or close to 0, therefore they are excluded in the final predictive model. Then here are some future improvements we can consider to incorporate transport type and also weather effects, and also remove the uncorrelation assumption.
Theoretically, due to the complicated map in the city, we can provide like up to hundreds of routes. The problem is to select the optimal route among these options. We use three-stage selection to determine our optimal route. First, we select the confidence on arrival time. The route with probability of on-time arriving exceed 95% would be chosen. Then we select the fastest routes with less transfer times. But if another route with more transfer time can save up to 5 minutes, we would replace with it. There is our result of scheduling from Sheng to Wartburg. The optimal route 1 is exactly the same with SBB. Trace 2 and trace 3 will take more time, while not necessarily increase the confidence to arrive on time because route 1 does not require any transfer. Another example is the scheduling from off-beacon to Daticom. Actually, the transfer takes place in P2. P1 can be avoided. The person can take subway from P2 directly. But here we take the train on P1 because it is more time saving. And that's our outline of work. Thanks for your time.